Hi, this is the third Alum video for the Aluminum Crystal Lab. It has been 5.5 weeks since we performed the 4 separate chemical reactions that synthesized alum from aluminum metal. In my first video, there seemed to be no sign of crystal formation yet. I was not able to pick up on any obvious differences from the beginning. In my second video, I still had no crystals, but there's a significant decrease in the amount of solution in the vial, proving that the solution was steadily evaporating. Since then, there's clearly been some crystal growth. I have exactly one well-sized crystal chunk in my vial, and the solution has also been evaporating at a steady rate, as it is now about halfway to the label, whereas before it started around up here or so. I've continued to keep my vial in the same spot next to the window, and the temperature has been consistent inside the room, although it has gotten much colder outside. Yeah, this crystal may have just been a late bloomer of sorts. Here's another look at my crystal. It is quite big. There's just one single chunk in there. To obtain large crystals, small seed crystals are first prepared. A well-formed seed crystal is then suspended in a saturated growing solution, and the solvent is slowly evaporated. By replenishing the growing solution, a big, perfectly high-quality single crystal of alum can be obtained. The temperature of recrystallization should be controlled as best as possible. If it is too cold, the crystals will be too small because the colder temperature will inhibit precipitation and cause the crystals to not precipitate out or be very impure if they do. My result was actually one giant high-quality single crystal of alum, which is quite interesting because it's despite the fact that I shifted the placement and the temperature at which the vial was kept at some point in the experiment. But this could be because I changed the conditions to be more ideal early on in the experiment, which facilitated the growth of the big single crystal. Also, since my crystal formed much more slowly than some of my peers who had multiple crystals by the second video, the quality of my crystal may be higher since it formed much slower. In X-ray diffraction, XRD, the interplanar spacing, also known as the D-spacing, of a crystal is used for identification and characterization purposes. D-spacing is the distance between successive parallel planes of atoms. In this case, the wavelength of the incident X-ray is known, and the measurement is made of the incident angle at which constructive interference occurs. Solving Bragg's equation gives the d-spacing between the crystal lattice planes of atoms that produce the constructive interference. A given unknown crystal is expected to have many rational planes of atoms in its structure. Therefore, the collection of reflections of all the planes can be used to uniquely identify an unknown crystal. In general, crystals with high symmetry, like an isometric system, tend to have relatively few atomic planes, whereas crystals with low symmetry in the triclinic or monoclinic systems tend to have a large number of possible atomic planes in their structures. To calculate the d-spacing for the largest peak on the graph, we would need to use Bragg's law. For this case, n is equal to 1, lambda is given as 0.15418 nanometers, 2 theta is equal to 20.75 degrees, which means that theta is equal to 10.375 degrees. After plugging these values into the Bragg's law equation, the n value, or the d-spacing, is 0.4 nanometers.